collaboration between the University of British Columbia and Imperial College London, and will be presented by Philip Edgecombe. The talk's title is Pico Lantern, a Pick-up Projector for Augmented Reality and Laparoscopic Surgery.
Thank you, Mr. Chairman, for the introduction. My name is Philip Edgecombe, and I'm an MD PhD student, and I'll be presenting in collaboration with the Hamlin Center for Robotic Surgery and presenting the Pico Lantern. There are many challenges in laparoscopic surgery. Those include instrument tracking, haptic feedback, and surface depth recovery for the purpose of surgical navigation. Within the context of depth recovery, techniques include computational stereo, structure for motion, and structured light. The Pico Lantern is a source of structured light for depth recovery, as well as a projector for augmented reality in surgery. Now, there's certainly been previous work by other groups in both of those areas. For example, in the top row, you see pictures of a laparoscopic structured light fiber optic probe. And in the bottom row, you see pictures of an augmented reality handheld projector for projecting augmented reality images onto the surfaces of organs during open surgery. So introducing the Pico Lantern, it is a tiny projector made to be dropped into the abdominal cavity through a laparoscopic surgical board, and then picked up by the surgeon to project light or images inside of the body. The intended uses are, one is surface reconstruction for creating a surface map of the surgical scene and registering it to the preoperative images, the detection of arteries via pulsatile motion, and finally, using the projector for the augmented reality display of the artery maps or other information to the surgeon. And I feel that both Al, the first speaker, and Peter have done an excellent job at motivating the importance of bringing preoperative data into the intraoperatively, as well as the importance of detecting arteries and using intraoperative and using pulsatile motion to do that. So the enabling technology of the Pico Lantern is the small projector. And what has really driven the development of that technology is the multi-billion-dollar cell phone industry that would like to be able to build projectors into smartphones. The projector that we are using is a Microvision ShowWX Plus projector, which I have in hand. It's about the size of a smartphone, has a resolution of 848 by 480 pixels, and a brightness of 15 lumens. The projector hardware components are a laser diode and a MEMS scan mirror, which means that the projector is in focus at almost every depth. So if we look underneath the hood of the projector, we see that it has a battery, the electronic components, and then the projector hardware components, which are the laser diodes and MEMS scanning. To create the Pico Lantern, we have taken the hardware components and separated them and put them within the housing of the Pico Lantern, which is a pick-up projector, and then connected it back to the Microvision projector via an electrical cable, which allows us to propose it for use in minimally invasive surgery. So let's see what it looks like. This is a video of the surgeon picking up the Pico Lantern and projecting a checkerboard pattern onto the surface of a kidney. Notice that it's small enough that it can be placed in front of the endoscope, and that the endoscope can track the optical markers on the Pico Lantern, and thanks to the registration of the projector, we know the transformation from those optical markers on the Pico Lantern housing to the projector optics itself. We have borrowed the concept of pickup, as in a pickup Pico Lantern or pickup ultrasound, from Caitlin Snyder, who's a PhD student in my lab who presented her intraoperative ultrasound, pickup ultrasound, here at MICCAI in 2012. We use two surface reconstruction methods with the Pico Lantern. The first uses a stereo endoscope and untracked Pico Lantern. This is very similar to conventional stereo laparoscopic surface reconstruction methods, with the additional advantage that the projected pattern provides additional texture for the stereo reconstruction. In the second method, we use a monoendoscope and tracked Pico Lantern. We determine the correspondence between the projected image and the projected image as it appears in the endoscopic camera, and also track the location of the Pico Lantern in the coordinate system of the endoscope, which allows us to do stereo triangulation between the two sensors. And importantly, there's a wide baseline, or there's a large distance between the two sensors, the Pico Lantern and the endoscope, which allows for accurate surface reconstruction. So we've made 3 prototypes for the purpose of this work. The first is a microvision projector with a checkerboard that is affixed to it, and that is the prototype that we used for our data collection. The second has a 28 millimeters in diameter. It has the identical components to the microvision projector and the same functionality. And the third is 17 millimeters in diameter, and we've built it, but it's still a work in progress. And our final goal is to make something that has a diameter of 12 millimeters or less, or half an inch or less, so that it can be inserted through a laparoscopic surgical port during laparoscopic surgery. So we determined the accuracy of 3D surface reconstruction of the Pico Lantern by imaging 3 objects, a plane, a cylinder, and a kidney. And for each of the objects, we moved the Pico Lantern to 5 unique poses. This is an example of the approximate geometry of the experimental setup. So let's look at the results. The relative error, defined as the average distance from the Pico Lantern surface points to the surface of the object of known geometry after the 2 data sets have been registered to each other, is as follows. For the stereo endoscope and untracked Pico Lantern, the error was between 1 and 2 millimeters. And for the monoendoscope and tracked Pico Lantern, we had sub-millimeter accuracy. When we move to absolute error, defined as the average distance from the Pico Lantern surface points to the gold standard surface, as determined by an Optotrack surface stylus, we see that the error is, for the monoendoscope, is 1 to 2, is about 1 millimeter. So next, I'll move to the more qualitative aspect of the study, which is the detection of a pulsatile artery. Now, the intended application is the detection of the aorta, the small mesenteric artery, the renal artery, and other arteries within laparoscopic surgery, but we use the carotid artery as a surrogate for our tests. So you're looking at a video, a 10-second video of the projected checkerboard onto the neck of a volunteer, and the location of the checkerboard saddle points, and by saddle points I mean the corner of the checks on the checkerboard, were tracked at a rate of 15 frames per second. In turn, that displacement data, and by displacement data I mean a bandpass filtered data at a range of 50 to 60 beats per minute, the magnitude of those coefficients is displayed to the surgeon as an RGB color map. It's an interpolated color map which is directly superimposed onto the checkerboard because that is where the displacement information came from in the first place. So if we look at the top graph, and that graph is showing the 10 seconds of displacement data from the saddle point that's shown by the tail of the arrow. And we can clearly see that the heart rate of the volunteer and the amplitude is approximately 1 millimeter. Whereas if we look at the second graph lower down, where the saddle point is removed from where the artery is, there's much less displacement, which is as expected. So if we take the RGB color map, which we can see on the right, and project it back onto the neck of the volunteer, this is what we see, and that's indicating the path of the artery. So, with 2 minutes left, I'm right on time. The future work includes real-time tracking of the projected pattern, clinical studies to really test the hypothesis that this can be used to detect arteries and the pulsatile motion of those arteries within laparoscopic surgery, as well as determining the accuracy of surface reconstruction for registering to preoperative information, and looking at the feasibility of using the projector to project artificial reality images. As well as we'd like to explore new applications now that we have this novel source of structured light, as well as a novel way to compute the surface map using a tracked Pico Lantern. In conclusion, we have developed and tested the Pico Lantern, which is a miniature calibrated projector for laparoscopic surgery. We've shown that it has an appropriate resolution, brightness, size, and form factor for laparoscopic surgery, and that it can be used for surface reconstruction. In fact, in terms of relative error, it gave us sub-millimeter error. It's compatible with stereo and mono endoscopes, and it incorporates a novel wide baseline method for surface reconstruction using structured light. So I'd like to end by inviting you to visit my poster at MCO4 to see the prototypes for yourself, and remind you that the Pico Lantern is a device that is looking for a starting position on the laparoscopic surgery team. Thank you very much.
Thank you very much. Very nice talk. And if there was a prize for the best name of a paper, Pico Lantern probably would get it.
Thank you.
The paper's open for questions.
The